Staring at a circuit diagram can feel like you're missing some kind of fundamental secret, right? If the basics of electricity have ever just left you scratching your head, trust me, you are not alone. So let's just dive in and clear up some of the biggest points of confusion once and for all.
Okay, so this is probably the first question almost everyone has. I mean, a light bulb is doing work, it's glowing, it's getting hot, so it just seems logical that the current flowing through it would get used up, right? But it doesn't. And we're about to find out exactly why. I promise you're going to see circuits in a completely new way after this. So, the root of all this confusion, it really just comes down to one core mix-up, and that's the difference between electrical current and electrical energy. Yeah, they sound similar, but they are completely different things. And getting this right, it's the key to understanding everything else.
This right here is probably the most common incorrect assumption out there. And it feels so intuitive, doesn't it? A resistor is literally built to resist, so it has to reduce the amount of current that's passing through it, right?
Well, actually, that idea is fundamentally wrong. The current doesn't get used up. And this one simple fact, it changes everything. So if the flow isn't decreasing, what in the world is actually happening inside that light bulb or resistor?
And here it is. This is the big aha moment. Let's really pull these two ideas apart. Think of current as the flow of traffic. It's just how many cars are passing a certain point on the highway. That number stays the same. Now, voltage, that's the energy each one of those cars is carrying. The cars themselves don't disappear from the road, right? They just drop off their energy package at their destination.
So the crucial point is this. A resistor, or a light bulb, it's basically like a toll booth for energy. The electrons arrive, they drop off some of their energy, which gets turned into heat or light, and then they just keep on going. The electrons themselves are not consumed, only their energy is.
Okay, to make this crystal clear, let's use the classic water pipe analogy. It's a great one. So imagine you've got water flowing through a plumbing system. The water itself, that's like our electric charges. The pressure pushing that water through the pipe, that's the voltage. And a narrow section of the pipe, a part that makes it harder for the water to get through, that's our resistance. So what's the current? Well, that's just the flow rate, how much water is passing a certain point every minute.
And this is the key right here. Think about it. The amount of water flowing through the wide part of the pipe has to be the same as the amount flowing through that narrow part. I mean, where else would the water go? It can't just vanish. But what does change is the pressure. You get a big pressure drop across that narrow section. And it's the exact same thing with electricity. The current stays constant, but the voltage drops. All right, so we've established that the flow is constant. So what does that mean for a simple series circuit? Where everything is just lined up in one single path. Now, Ohm's law is a total cornerstone of electronics, but man, it gets misinterpreted a lot. People see that formula, I equals V over R, and they think, okay, more resistance right here means less current right here. But that's looking at the circuit in tiny little pieces instead of as a whole system. Here's the correct way to think about it. The total resistance of the entire circuit is what tells the power source, like the battery, how much current it can even push out in the first place. It's like setting the master flow rate for the whole system. And once that current is flowing, it's the same, everywhere, all along that single path. So why must the flow be constant? Well, think of it like single-lane traffic on a highway. The cars can't just disappear into thin air. Electrons are exactly the same. They literally have nowhere else to go. If they started to pile up in one spot, you'd get this massive electrical traffic jam, this huge repulsive force. Nature just instantly and automatically balances the whole system out so the flow is perfectly uniform everywhere. All right, let's move on to our next big point of confusion. I'm sure you've seen this. You look at a circuit diagram and the arrows for current are pointing one way, but then someone tells you that the electrons actually flow the other way. So what's going on there? So here's the breakdown. What we call electron flow is what's physically really happening. These tiny negative particles, electrons, are pushed away from the negative terminal and they flow towards the positive one. Simple enough? But for historical reasons, we also have what's called conventional current. And that's just a model that pretends positive charges are flowing from the positive terminal to the negative one. And yeah, it's a totally fair question. If we know it's technically backwards, why on earth do we still use it? It just seems like it adds a whole layer of confusion, right? Well, the answer is surprisingly practical. See, by the time scientists really figured out the electron's role, decades of engineering formulas, all the symbols for components, entire textbooks, They were already based on that positive to negative idea. And here's the real kicker. It doesn't actually matter. Whether you imagine positive charges flowing one way or negative charges flowing the other, all the math, all the analysis, it works out exactly the same. The only rule is just pick one and be consistent.
Okay, so far we've really only been talking about these single-path series circuits. But what happens to our steady flow of current when we suddenly give it a choice of paths? Well, that's the core difference between series and parallel circuits.
So as we've said, in a series circuit, it's a one-lane highway. The current is exactly the same through every single component. But in a parallel circuit, that highway splits into multiple lanes, or branches. So when the current gets to that junction, it has to divide itself up among all those different paths. And hey, our trusty water pipe analogy makes this super clear. A series circuit is just one long, continuous pipe. The flow is the same everywhere. A parallel circuit, that's when that main pipe splits into 2 or 3 or more smaller pipes. The water flow has to divide between them. It's the exact same principle for electricity. The total current splits, and the amount that goes down each path just depends on the resistance of that specific path.
So, let's recap the golden rules here, the main takeaways. Number 1, resistors and light bulbs use up energy, which we measure as a voltage drop. They do not use up the current, which is the flow. Number 2, current has one physical flow, but 2 different labels we use for it. Just pick one, electron or conventional, and be consistent. And number 3, current follows one single path in a series circuit, but it splits its path when it hits a parallel circuit.
Look, if you can really get these 3 ideas down, you've moved way beyond just memorizing formulas. You're actually starting to think about how electricity behaves, like an engineer does. So the only question left is, now that you have this clearer understanding, what are you going to build?